Hi everyone, welcome to my talk today. I'm Jinlai from University of Pittsburgh. So today I want to talk a little bit about one of my overworks, resilient stream processing in edge computing. Before going to the details, I want to discuss some background information. Here, as you may know, we are already in an IoT era. The IoT devices are being deployed everywhere around us. In these years, the experts predict there will be around 20.4 to 31 billion IoT devices being installed. And predicted by the IHS markets, that there will be around 125 billion IoT devices by 2030. Beyond that, the IoT market is increasing very fast. And most importantly, there's more and more data generated by the IoT devices. That's predicted that there will be around 79.4 zettabytes of data generated by the IoT device, which is nearly half of the 175 zettabytes internet combined by 2025. So with the more and more IoT devices being installed around us, and with the developing of the IoT applications, they enable the new possibility for us to achieve a better life. As shown in the figure, that's as you can see, there are a lot of kinds of IoT applications. On one hand, the data volume generated at the edge of the network is increasing very fast with the deployment of the sensors and IoT devices. And on the other hand, there are various applications in the IoT area have a strong demand for low latency computing. For instance, that's the virtual reality or augmented reality applications needs which use the head tracked systems require latency less than 16 milliseconds to achieve perceptual stability. Similarly, there's other strict latency requirements from the other IoT applications. And beyond that, there are various requirements. For example, the throughput, the security and privacy requirements from various IoT applications. In conclusion, both the low latency and other requirements need to be handled properly, which introduces new challenges for the infrastructures and the platform to handle the application. So that's stream processing is coming into picture, which can achieve both the low latency and high throughputs. There are a lot of projects developed in the recent years. For example, the Storm, Flink, Sparks of streaming, which are being used by thousands of companies to meet their strict requirements. And for example, that's Facebook's stream processing engine named Scribe processes 2.5 terabytes input data per second. So within the recent number of IoT devices and IoT applications, the IoT and the big data challenges are emerging, which includes the volume. That's the data generated is increasing very fast, and the variety, which means that there's more and more kinds of applications being developed for the IoT era. And there's last dimension is velocity, which means there's more strict latency requirements needs by the applications. And also there are other challenges which is previously in the slides. So cloud computing has been very cost-effective solution to address several computing needs. However, clouds fail to meet low latency requirements of the modern computing applications that may have a strict latency guarantee. So that's the edge computing is proposed here to complement cloud computing to cover the challenges. That's the cloud's hardest to tackle. So what is edge computing? Actually, edge computing is a model that provides an additional layer of computing structures for storing and processing data at the edge. So that it allows low latency applications to meet their requirements. And they have also provided other features such as less network bottleneck, and this data can be further processed locally, which may provide other benefits such as privacy. However, they also have some, they make the environments more complex, so that's for example, most of the IoT devices have lower reliability than the servers provided by the cloud provider, and also that's the workload may be highly dynamic. So to deal with the challenges, we may have many solutions. One of them may be directly deploy the stream processing engine in the cloud. However, it cannot achieve low latency. But if we deploy the stream processing engine in the edge computing environments, so it may bring new challenges, such as that the stream processing engine needs to understand the heterogeneous nature of the edge resources. And also that's because that's the stream processing engine, they have already have some fault tolerance mechanism. So this kind of fault tolerance mechanism needs to adapt to the edge stream processing, edge computing environment. So in this work that we propose a resilient stream processing framework for the edge computing. As I already discussed, the fault tolerance is very important for achieving low latency stream processing in edge computing. And as you may know, that the failure is very common in the edge computing environments. That's for example, that's the IoT device may disconnect from the network, or may maybe a lack of battery. So that's the fault tolerance mechanism is needed for edge computing environments. And currently, for the stream processing engine, there are already some fault tolerance mechanisms, such as the checkpointing and the replaying mechanism. However, that's the recovery cost is very high, which is not tolerable when the latency requirement is strict. And there's a nature idea that's how about we apply that's the active replication to the picture, which is actively replicates the of the application to achieve a better recovery cost. However, this is a promising idea, but it may increase the resource usage. So that's in this work that we propose a resilient phase plan generation to take the advantage of both the checkpointing and the active replication to optimize the recovery cost. And in addition, that we propose a resilience well scheduling mechanism to decide the placements of both the operators and the fault tolerance components. So that you may have a question that's why we need to propose a two phases mechanism, and why that we need the scheduler to deal with the to understand both the operators and the fault tolerance components. So here that I want to give a simple example for that. For example, here is a stream processing application, which is already deployed in the edge environment, which has two smart gateways and one micro data center server. And we already applied some fault component to it. And for example, we already actively replicate the counter operator. And we already have that's the checkpointing mechanism and the replaying mechanism that's a backup of the application as shown here. That we have the checkpoint store and the security track of the completion of the tuples. However, if that's the scheduler does not understand the application and the edge computing environment, so it may have some degradation of the performance of using the default scheduler. So here for example here, that's because of that the scheduler does not understand the edge computing environment, so it may and also the fault tolerance components, it may deploy the primary operator, which is the counter operator with the same node of the active location, which may make the schema inefficient because of that. If that's the counter operator fail, it may also make that the active replication fail, which is very inefficient in the current example. So that we propose two phases mechanism. As shown here, that in the first phase, that in the region we propose a mechanism named the resilience physical plan generation, which first we apply the checkpointing and replaying mechanisms to all of the operators. As shown here, that we add the checkpoint stream, the state management for all the stateful operators, and also that's the security track or the completion of the input tuples. And also here that we decide which operator to be actively replicated by the three dimensions. First, we consider that's the failure probability of each operator by using a method also for system, and we also have to consider the recovery cost, which is goes by the profiling, and it's just the time that's between that's the operator fail and the output is generated from the failure. And we also consider that the fault tolerance budget to to meet the fault tolerance budget to decrease the resource usage of the fault tolerance mechanism. So here in the example, that in the table that we have the failure probability, the recovery cost, and then we can calculate the expectation of the recovery cost by multiplying these two number. And then in the example that we choose the counter operator to be actively replicated. And then we compare this the fault tolerance budget with the current usage of the fault tolerance mechanism, and to choose the other operators to be replicated also. And in the second phase, that we propose the resilience well scheduling mechanism, which based on the output from the resilience physical plan. So that's here that we deal with different fault tolerance components with different mechanism. For the checkpoint related components, for example, the checkpoint store, that we compare the distance between all the state for operators and the segment store to decide its position. And for the asymmetric tuples, we place it at the gravity center of the application, so to minimize the weighted cumulative latency for tracking the tuples. For each active replication, we place it near the primary operator, but within another node to avoid that correlated failure. In the experiments that we deploy testlets in an OpenStack cluster deployed on 10M510 servers in Cloud Lab. Here that we have 3 tiles edge computing resources. There's 1 mega data center, 5 micro data centers, and 14 smart gateways. And we also divide the networks in the topology and define the bandwidth and the latency between them. And we tested the performance with an accident detection application, which has 4 operators. The first operator, that's the source operator, takes the input from the sensors, and we deploy 1 stream generators in each of the smart gateway to emulate the data sources. And then that's when the tuples taken into the application, it's filtered by a filter and to detect the car which may have accidents, and the aggregator aggregates the car information by the location and the windows, the time windows, and then that's the results are stored in the database. And for the methods that we tested, these 2 phases of different methods. For the fault tolerance mechanisms, we tested with the checkpoint only mechanism for replication, and also our resilient physical plan generation mechanism. And for the scheduling, that we compared our mechanism with the default scheduler of Apache Storm, which is a round-robin resource-aware scheduling mechanism. And here's the experiment results. We first compared the performance during fail-free and fail-injected conditions as shown in the left 2 figures. You can see that our mechanism and the full replication are not influenced. But the checkpoint only mechanism that does not output anything during the recovery, because that's their operators need time to recover from fail. And as shown in the figure, that we can see that if we only apply the resilient physics plan, the application will also be influenced by the correlated failure. And in the experiment, it shows that it maintains half of the throughput. And we then evaluate the latency, compare the latency distribution between overall and during recovery in the right 2 figures. And we can see that our mechanism performs best, and then that's the full replication. And we also compared the success rates and throughputs of those mechanisms. The result is similar to latency. That's all mechanism and full replication performs better than the others. And at last, we compared the resource usage. For all the sources, we can see that full replication uses much more resources than the others. For the memory usage, that we can see that for all mechanism, that's the memory usage is slightly increased during when the input rate is increasing. And all mechanism use more network bandwidth than the other two, which is because that we place that's the active replication in different nodes. So thanks. If you have any questions, please you can contact me by the email on the slides. Thank you.